Welcome back. In this video, we're going to explore the concept of optimization. In optimization, what you're going to be doing is you're going to be given a problem where you're trying to maximize or minimize a measurement or a cost or something like that, and you're going to have some sort of constraint equation. So you're going to have an equation which is going to be a constraint equation, and then you're going to have an equation which is going to be an equation which you're trying to maximize or minimize. You plug in the constraint, take the derivative, so on and so forth. Make sure you read the problem very carefully. Sketch a picture if you know it. Write down all the facts that you know. Find any missing facts that you might not know that would be helpful. Determine which variables are trying to be maximized or minimized. Find your critical numbers, and then verify the extrema in terms of the maximum or the minimum. In my first example, what I have is I have this piece of metal which is 12 inches long, and I'm going to turn up the sides, so I'm going to make a rain gutter like on the front of your house. And when I turn up these sides, I'm going to call these pieces X. I'm going to let this be Y. So 2X plus Y has to be the 12 inches. Now, what I'm going to do is I'm going to solve this for Y equals 12 inches minus the 2X. And what I'm going to do is I need to maximize the area of this. I'm not going to really worry about the volume. I know I want the water coming in here, but the volume is going to go how long your house is, like 30 feet or 25 feet, whatever it may be. So I'm really just trying to maximize this area, which is X times Y. I'm going to plug in that constraint, which is X times 12 minus 2X. And then it's easiest, before I take the derivative, to go ahead and distribute that X. So it's going to be 12X minus 2X squared. Now take the derivative, a prime, which is going to be 12 minus 4x, and set that equal to 0. We have a potential maximum point at a cut of 3 inches, or a turn up of 3 inches. If I put in a number line, do my first derivative test, if I plug in a value below here, it'd be positive, above here it'd be negative, so that is a maximum point. So then the y value would be 6 inches, and those would be the dimensions that would maximize the water that the rain gutter would hold. In my second example, what I'm doing is I'm taking a piece of cardboard that's 25 inches long along one side and 20 inches long along the other side. And I'm going to cut out this corner that is x units, so a square that's x by x, and I'm going to turn up those corners along the dotted line to form an open box. And so when I do that, I want to maximize the volume of the box. So really the key is to maximize the volume of the box. The x corner that you're cutting out is going to be the height, and then the width and the length are going to be 25 minus 2x and then 20 minus 2x, because you're cutting out a distance of x in this direction and in this direction, and so that's why it's 25 minus 2x, and then the same thing on the other side. When you multiply that out to get the volume, I got 500x minus 90x squared plus 4x cubed. Take that derivative, and I got 500 minus 180x minus 12x squared. Set that equal to 0. And this one, you don't have to ever use quadratic formula. So I just graph this and calculate the 0 on my calculator, and I got x to be 3.681. And that would be, in this particular case, inches. And that's the cut that's going to maximize the volume of my particular box. There might be another x value, but it falls outside the domain. The domain in this equation has to fall between 0 and 10 inches. In my next example, I have this time I'm going to try to minimize my cost. I have a cylinder, okay? And the first thing I know is I have a capacity of 24 pi inches cubed. So the velocity of a cylinder is pi r squared times h, and that equals 24 pi. Simplify as much as possible, so cancel those pi's. And then I would solve this for h. This is going to be my constraint equation. So h is 24 divided by r squared for this particular cylinder. Then I'm going to generate an equation based upon the cost. And the cost is going to be 15 cents per square inch for the bottom of the container. And I have an open top, so the bottom of the container the cost is going to be 15 cents per square inch for the bottom circle, which is pi r squared. And then it's going to be 5 cents per square inch times In this particular case, it's the sides that go around the sides, so it's what we call the lateral area of the cylinder, which is the circumference of the base, 2 pi r times h. And again, like I was saying, you don't have to memorize these formulas. This is the formula that I'm going to simplify as much as I possibly can. I'm going to plug in that 24 over r squared for h right here, so I have the cost all based upon the radius. So the cost, and this is just a lot of simplifying, is going to be 0.15 pi r squared. This is going to become plus 0.1 pi r times, and then I'm going to put in the 24 over r squared here. Before I take my derivative, I'm going to ultimately end up writing the cost of this as being 0.15 pi r squared, and then plus 2.4 pi r to the negative 1. And then take the derivative. When I take the derivative, it's going to be 0.3 pi r minus 2.4 pi r to the negative 2. We want to set that equal to 0. And when I did that, what I found is that r would be 2 inches. And then to get my h value, I plug that 2 inches right back here, and h would be 6 inches. In my next example, I'm going to work with Pythagorean theorem, and I have this north-south and east-west highway that's traveling, and I have my cars traveling. And so let me just sketch that real quick. So I have one car going this way. I have one car running along a north-south, and I want to know when they're going to be closest to each other. So I'm trying to minimize that distance, that Pythagorean theorem distance. So if I say that this one right here is he's traveling east at a constant speed of 20 miles per hour. So this part right here, my x value is going to be 20t, where t is in hours. And then this guy is up here, he's 50 miles away, and he's 2 miles away, and he's traveling at 50 miles an hour. So my y value is going to be 2 minus 50t, and then z is the relationship that I want to minimize. So the relationship between the three variables is Pythagorean theorem. So z squared equals 20t quantity squared plus 2 minus 50t quantity squared. I simplified that equation, so z squared equaled, when I got this, my z squared would be 4 minus 200t plus 2900 t squared. Take the derivative. You technically would take this, well, let me do it this way. This is not squared, make that to the 1/2 power. I really don't have to worry about that. When I take this derivative, it's going to be the derivative of the inside part, which is going to be negative 200 plus 5800 t, and that's what I really want to know, where that equals 0. It's going to be over 2 times 4 minus 200t plus 2900 t squared. I'm not worried about where that derivative is undefined, because that's going to be the endpoints of my domain, so I don't need to worry about that. I just need to worry about this right here. When I do that, when I set that equal to 0, I found t to be 0.034 hours. And then they ask you what is the shortest distance as well, so you put that into this equation right here, and I found that that shortest distance is going to be 0.743 miles. I'll explain this part right here a little bit more to you, why that denominator doesn't matter when we come to class. And then finally, in my last example, I'm planting some apple trees. And I have 25 trees in my orchard. As I plant more trees, the number of apples per tree is going to go down. So what ends up happening is I need to write an equation for the apples in my orchard. So it's going to be the number of trees times apples per tree. So the number of trees in my orchard is going to start at 25, and I'm going to add T to it. The number of apples per tree is going to start at 700, and then for every tree that I plant, I'm going to lose 20 apples per tree because of natural resources. Again, before I took the derivative, I simplified this. Then take your derivative, a prime, which would be 200 minus 40t. Set that equal to 0, and t equals 5. And t represents the number of trees that you're going to add per acre. So if I wanted to know how many trees should be planted per acre to obtain the most apples, then I want 30 trees per acre. All right, so optimization, a lot like related rates, takes some practice. You need to write down everything, draw pictures, talk about it, think about it, walk away from it, come back to it. Takes a little bit of time, but you're just optimizing equations. You're maximizing equations. So find your constraint, develop an equation which you're trying to maximize or minimize, take the derivative, set it equal to 0, and work from there. See you soon.